All right, this is the 8.1 notes, and it is on theoretical and experimental probability. So the objective, students will be able to determine theoretical and experimental probability of an event. So why study probability? Well, here's a quote from our textbook. Uncertainty and randomness occur in many aspects of our daily life. Decision-making in the worlds of business, investment, agriculture, and industry, healthcare, and all aspects of real life is based on expectation and prediction. Having a good knowledge of probability helps you make sense of these uncertainties, understand risk, and make better decisions about the future. So the study of probability helps us to understand the degree of uncertainty of something happening. A probability experiment, or just an experiment, is something that has an uncertain result. An experiment or trial is the process by which we find out information about events by collecting data in a careful manner. An event is a single result of an experiment, so getting a tail, so the experiment would be tossing a coin. Rolling a 5, the experiment would be rolling a 6-sided dice. Choosing a king, the experiment would be picking a card from a standard deck of cards. Getting an even number, the experiment could be spinning a number spinner. The probability of the occurrence of an event can be presented using words, but more useful is a value from 0 to 1. 0 represents impossible and 1 represents certain. We would write P of A to represent the probability of event A occurring. And so we would say that the probability of event A occurring has a value between 0 and 1. There are two main ways of finding the probability of an event: theoretical and experimental. The theoretical approach to probability is based on a number of events where the likelihood of each event occurring is known. The set of all outcomes in an experiment is called the sample space of that experiment. It is denoted by a capital U. The notation N of U represents how many elements are in the sample space. So here's an example. A fair dice has 6 sides, all of which are equally likely to occur. The list of equally likely outcomes is 1, 2, 3, 4, 5, 6. We would write N of U equals 6. If the event A is rolling a 6, then the number of elements in that event would be 1. There's only 1 6 on a dice. So then, the probability of getting A to occur, the probability of getting a 6, would be the number of elements in the event over the total number of elements in your sample space. So this is 1 over 6. So generalizing this, the theoretical probability of any event A is the probability of A equals the number of elements in A over the number of elements in your sample space. Expected number of occurrences. If you roll a 6-sided dice 6 times, you would expect to get a 6 once. For 12 rolls, you would expect to get a 6 12 times 1 over 6, or 2 times. If the probability of an event is P in N trials, you would expect the event to occur N times P times. So let's look at example 1. A fair 20-sided dice with faces numbered 1 to 20 is rolled. M is the event defined as the number obtained is a multiple of 3. So this is going to be the number of elements in M over the total elements in your sample space. Well, let's think a moment. The multiples of 3 up to 20 is 3, 6, 9, 12, 15, and 18. So that's 1, 2, 3, 4, 5, 6. And then there are 20 numbers on this dice. So that's 3 over 10, or 0.3. Now, what if the dice is rolled 100 times? Out of the 100 times, How many times would you expect to get a multiple of 3? Well, you'd take 100 times your 0.3, so we would expect it 30 times. All right, we have something called a relative frequency. And a relative frequency is the ratio of the number of times an event occurs to the number of occasions on which it might occur in the same period. We also have the law of large numbers. In an experimental probability, the probability of an event is based on the outcome of a series of trials. As the number of trials increases, the probability will get closer to the actual probability. So you can use relative frequency as an estimate of probability. The larger the number of trials, the closer the relative frequency is to the actual probability. So let's look at example 2. The colors of cars passing the school gate one morning are given in this table to the right. It says estimate the probability that the next car to pass the school gates will be red. Well, you're going to look at your table, and there are 26 out of 110. So that's 13 over 55, or approximately 0.236. Using this information, if 150 cars were to pass the school gate the next day, estimate the number of red cars expected that morning. So go ahead and pause the video and see if you've got the hang of it. So you're going to take 150 times 13 over 55. So I got about 36 cars, 35.5. All right, the color of cars is recorded on the following day. So this is now day 2. This was day 1. It says, what is an improved estimate of the probability of the next car to pass the school gate being red? It would be awfully tempting to say 20 over 92. And that's not going to be a very good estimate. That's only the estimate on day 2. So watch what you can do. You can take 26 red on day 1 plus 20 red cars on day 2 over 110 plus 92. This would give us a much clearer estimate. So the probability that the next car would be red would be about 22.8%. All right, 2 events are complementary if exactly one of the events must occur. If A is the event, then A prime is the complementary event of A. So here's an example. An ordinary 6-sided die is rolled once. Determine the probability of getting a 6 would be 1 out of 6. What's the probability of not getting a 6 is 5 over 6. So here's something interesting to note. The probability of A plus the probability of the complement of A should add up to 100%. It's an either or situation. All right, this was a quick video. We're done.